Okay, so this is not an AFM, but this is a pipette. In fact, it's a capillary tube pipette used for nanolithography. But I choose it because you could see the cantilever coming out of the tuning fork. So the tuning fork itself is 2 tines. It's a piezo element enclosed with metal electrodes. We vibrate it either internally or externally. So due to its high Q factor, it gives a very strong response in the resonance frequency, and it's very good then to use it for AFM feedback. We attach the tip or different type of probes, AFM probes, NSOM probes, thermal probes, and different other probes to the tuning fork rigidly, and that will be part of the tuning fork. And then this will be used, in fact there's no optics, just this small piece will be used for AFM feedback. Okay, could be in amplitude feedback mode or in phase feedback mode. So you can just move it, and if you look to this side, you'll be able to see the cantilever, and if your eyes is strong enough, you could see even the bend of the tip. So the tip is
young, you can see it.
So it looks like this, in fact. Okay, so this is the cantilever and then bent area. So tuning fork in this case will be working in normal force. You know, when people don't like tuning fork because it works in shear force. Shear force means that the tuning fork is this way, and then you have a straight probe, and moving the vibration mode is in this way. While your topography is in z-axis, so you don't want to have a shear force because then you can easily break that in. So then this solution is really nice using a bent probes. So where it can bend with this cantilever up and down, give it enough flexibility without breaking the probes. So it could be glass probes, or it could be NSOM probes, or it could be even either silicon probes attached to these tuning probes. So they can host different type of probes for different AFM or SPM applications. Okay, so we're going to excite the tuning fork externally. So on the AFM head, in fact, this is the part. This is the AFM head together with the sample scanning stage. So in this system we have 2 AFM heads, okay? Right tower and the left tower. Every one of these towers also include a tip scanning stage. So in general you have one sample stage, one to move the sample in X, Y, and Z, and additional piezo for the first tip in X, Y, and Z, and the same for the second station. So you could do up to 100 microns in X, Y, Z for the lower one. Notice also Z. Due to the flat structure of the 4 piezo elements, you can do up to 200 microns. Normally, most of the AFM system uses between 5 to 20 microns. So this is good for rough surfaces, for cells, for for like fibers, textile fibers. Or wood fibers, plastic fibers, that would be good to cover with AFM such roughnesses.
So the AFM with the laser deflection, where is the laser?
There is no laser deflection here.
Okay.
It's using the tuning fork for the feedback. Okay?
Yeah, okay.
So in laser deflection,
I thought you had it integrated.
No, not
as
yet.
well.
Not
Okay. Yeah.
in principle, you could add it. You could have an optical module just to add it here. You will have the beam coming through the objective and reflected back to the photo detector, which also will sit here in an intermediate module between these two components. Okay? So you could have a separate AFM. Thank you. So you could have an AFM system working in optical feedback, an AFM system working with tuning fork, and you could have a system working with tuning fork, and it's still possible to use optical feedback as well. Yeah, so this system is, we're going to do a basic AFM operation, okay, just to see the standard operation of the system. But this system, in fact, is capable to do multi-probe operation. The previous experiment which we were doing is bringing one probe to feedback, delivering the line into the surface, and then bringing the second probe in close proximity to that, and scanning, starting from this point, from the first probe point, collecting the topography and collecting the near field optical signal. Now the signal, one fiber probe, then before we go to the AFM, let's see this. So this will be the NSOM fiber probe, in fact. So one probe will be, this side will be connected to the laser. So you will have a very small light source coming out from this position. You can use it for NSOM measurements for high resolution optical imaging, or for optical nano manipulation, or activating a specific location for the sample. Could be 50 nanometers, 100, up to microns. Okay? So this will be delivering the light. A similar AFM probe will be mounted on the second tower, the second AFM system. The light, this probe, the second probe will come close to the first one, collect the near field light, coupled through the fiber. The fiber is connected to a detector. Could be PMT, it could be an APD detector. Okay? So this will be near field injection of light and near field collection with two NSOM fiber probes, where you can easily use two piezo stages, two AFM independent systems to bring them close enough to each other and to do this task.
How close do you typically get the NSOM probe?
Touching. Yes, because when they are in feedback with the sample, so you have a Z feedback level which you can easily see and monitor with this system. So when you bring them, when you offset the tip, you will see that the Z feedback start to change. They start to feel each other. So you know that this is the point where they are touching each other. So it's yeah. So this is what we were doing till now from the morning. In fact, I think that we still have one picture like that. Yeah. So this was the AFM, and this was the NSOM image on top of a gold strip. Sorry to shift to the other subject. See these lines here. This is where we were touching with the first step. Right. So we know this is the 0 point, and then from there, we scan back from the the fixed tip or the illumination. So this is an AFM. This is an NSOM.
But that's AFM with the NSOM probe.
Yes, that is true. It's an NSOM with an AFM probe, and this is the NSOM which is detected there. The NSOM, the optical signal is detected. It's connected directly to an APD, or it could be connected to any spectrometer. In fact, you could do spectroscopy, or you could connect it to the DCSP. Then you do lifetime measurements with these APDs. I think we're still using the same APD.
You'd have to use PMT.
It is the PMT, yeah, with the...
Well, I can use APD too.
Yeah.
Yeah, the APD...
The right kind.
Right.
They have short...
Right, it's a
function.
Yeah.
MPD can be used too, but they have to be to that point.
Right, yeah. So...
PMT is also... This is a regular, this is analog PMT.
Right. No, I mean, it's still TTL.
TTL pulse, so it's a single photon counting pulse.
So it's the sensitivity of the APD is much better here. It's the quantum efficiency at 650 reaches 60%. While here it's only 10%.
In that case, that APD didn't work for TCP because it has a very thick absorption layer for your photons at 650, which means it has very high instant response function of 5 million picoseconds, very slow.
Yes.
Do you record the height and the SNOM
with the same tip?
At the same time, or
yes.
do you trace
the same,
like
no.
the high and you trace?
Same time. For
time.
each pixel, because the NSOM because the AFM, the NSOM signal from the instrument, from the AFM perspective, it's an AFM tip.
Yeah.
It will give you topography images, and you take the signal from the detector and you couple it to an auxiliary input here. So it will be synchronized with the AFM. So you could in fact use, you could couple another signals like electrical signals or thermal analog signals to the system, and you could choose up to 16 channels and monitor these simultaneously.
Okay.
So synchronized pixel by pixel. Okay, so we're going to mount an AFM probe.
The only downside with using the NSOM probe as an AFM probe is that it's lower resolution because you have a larger tip than you would with a typical AFM probe.
Okay, so let's take the probe.
What kind of lamps do you have for the camera? Is it a C1?
This one?
No, for the camera. Just the TMT is a C-mount?
No, this is not C-mount. This is a mount which we built ourselves, so it's matched with the tube length of the microscope. So, and also it has a housing, it has an XY stage, so you can place it in the correct position. You know, if there's a tube length here, then you could put filter inside here, and the Z position here is matched with the tube length.
What's our TMT?
The model itself, I can't find that out. So it says MP942. So,
Solitas used to be EG&G. Perkin-Elmer, EG&G, Perkin-Elmer, Key-Optic, Accelitas. There you go. And or Oxford.
So
Moving places.
we just put the sample on top there, no need for vacuum or no need for fixing, just gravity. We put the tip in there. We check the resonance frequency first. It's an automatic procedure to do that, but we can do it also manually. We're going to work in, what is the resonance frequency? Is around 40. Okay, so this is the peak and the resonance frequency. Normally, the pure tuning fork gives a resonance frequency at 32 kilohertz. And when you add the tip and add the glue, you change the mass and the balance between the two times, so it becomes slightly different. Okay, so we're going to work in phase feedback mode. With tuning fork, this is the good thing, which is not possible, in fact, with the with optical beam down system. You directly have a frequency modulation. In optical feedback system, you work in amplitude feedback. Here you could work with amplitude or with phase. The advantage of working with phase, you know, phase changes are much faster than amplitude changes, especially with the high Q factor of the tuning fork of few thousands. Okay. Now, but additionally, when you work with the phase, you keep the amplitude not changing, because the amplitude is about few nanometers in that case above the surface. So the phase changes before the amplitude start to change. Okay, so any change of the amplitude during the measurement gives us, in fact, an effect on, gives us an information about mechanical properties. Okay? So you scan with phase, you get the error signal, you get the high topography information, but the amplitude channel gives you additional information about mechanical properties of the sample. So you don't need to do any force measurements like you do a force measurement, force distance measurement at every point. Here you have you're monitoring only the amplitude, and it will give you a nice representation for the elasticity of the mechanical properties of the sample. So that's additional advantage of tuning. So then we shift to phase. Select the zero value here, which is the resonance frequency. And then when we're ready to approach, we just put the tip in the correct place above the surface and we'll be ready to go. So I move the tip in. There is a rough motion first, so we slide it out to put it in the, like in case of we have two probes. So before starting approaching, let's see some optics here. So as I said initially, this system was designed to be integrated with optics. So we have a clear optical axis from top and from bottom, so where one can see the exact contact point of the tip with the sample. Now it's due to the flat scanning stages from top and bottom for the sample stages and the tip stages, and also for the probes themselves. So we will soon see the tip itself. It's made of glass, pulled under heat to form a very sharp end, and then it's bent. So the bend gives, it's about few tens of microns between the cantilever and the end of the tip. So when you are focused with 50x objective on the tip, you don't see any obscuration due to the cantilever. Also the bent angle give it to be exposed, so you can easily see the tip touching the surface from top. Now this is I mean, you could see in many systems from below, but only few systems can give you a nice or clear optical access from top. And that is very important because most of the samples for AFM are opaque. So that it's very important. So that's why people use, for example, side view, but still not effective. I mean, if you work with optics, you better work, in orthogonal directions, and not in an angle. So now we're starting from the 10x objective. So we see with the CCD here, you see the upper tine of the tuning fork. If we go down, it's the lower tine. If we go down with the focus mode, we'll be seeing the cantilever. Okay, so this is the cantilever. If we go down, you'll see the end point of the tip. This is with 10x object. Okay, so we switch down with the focus. You'll be able to see the sample. So this is the sample. This will be going down. So let's approach the tip. Not directly to the surface, slightly before, like a few microns above the surface, and then when we switch to 50x objective, so we'll have better field of view, and we'll see the advantage of these exposed tips when they're touching the surface. So the tip is coming down now. It's the approach process is done with with a Z stepper motor, and this is linked also to the Z piezos. So we ensure that the engagement with the sample is done in a gentle fashion. So the tip is coming down. So we could adjust the speed of the approach. We know that it's quite far away from the surface. Okay, so this is the tip. Now let's switch to the objective. This is the tuning fork edge, which we have seen before with the 10x. And this is the cantilever starting from here. If we move it back, adjust the focus slightly. You will be able to see, if we go down with the focus, you see the bend, and then the end of the tip. Very small, tiny spot. Okay. So then we bring it down to the sample. Okay. So we can, okay, we continue the approach. So the tip is coming down, and all the signals and the voltages that we are applying in X, Y, and Z can be easily monitored here, and they are accessible, similar to the lock-in amplifier signal. So in case you want to synchronize or to work with these signals externally, you can easily get them from the outside. We will shortly explain also about that. So is the tip in feedback? Yes, it tells me it's in feedback. Also the software tells it's in feedback. But where's the tip? So this is the beauty of the tip. This is small, little point. So just keep in mind you have the standard silicon cantilever with the Permian apex going down. So you will not be able definitely to see such type of thing. Now this is true for AFM tips, for NSOM tips, for thermal tips, for electrical tips. You can easily have them exposed, so you can combine AFM with optics easily from top and from bottom. And you can combine AFM with other modes of operations, of SPM operations, easily with this type of access. accessible by multi-probe, for example. Like you could have one probe AFM, one probe for NSOM, or one probe to provide heating, and a second probe to detect thermal transport. Okay, so we run feedback here. So let's scan, like let's say maybe 5 by 5 microns. So the sample will be moving now, because we're using sample scanning mode. There's a slope on the sample, because you glue the sample or you put it on the lower stage, so it has some tilt. You can apply a hardware compensation by simply applying a Z offset, so it brings this, this bias or this. Stop that. I think I used the wrong calibration formula. I'm still using the TIPS camera. So here, using lower scan rates. So it start to scan. So you can see the X is the fast axis, Y is the slow axis, and this is the feedback. Monitoring this value is very important because it gives you information about the quality of the feedback. If this is stable, or if this is drifting, or if something wrong is happening. It's more important in NSOM where you have optics, heating, and other areas. So this is the topography being built line by line. Now we see here two lines. One is trace and the other one is retrace. Okay? So every line is scanned twice, from left to right, and then from right to left, and then moving one pixel in one, then left to right, right to left. The advantage of having these two lines is important, in fact, in AFM, because you could correlate between them, if they're matching or if they're similar. Or sometimes if you have an artifact or if you have a noise, it would appear in the trace and wouldn't appear in the retrace. So you could easily adjust the gains and work with the, optimize your AFM setup based on that. So this is the AFM image being the, we'll wait a few more lines to see what's going on.
Do you see a big effect if you slow down your scanning speed?
Yes, definitely. The slower is the better, in fact, and you will get, because then you have, the gains are more relaxed, especially the integrator gain. Because the higher the integrator gain, which sets the response of the feedback, how fast you apply the feedback, the faster this response is, the more noise you're getting, specifically the overshoots at the edges. So if you use a slower scan, in fact, it's a low pass filter, and you cut these overshoots. Okay, so this is the you can do different filters during the scan. So you could scan. Okay, so this is the building line by line. Jump to view. You could change colors, change filters, and then not image processing yet, but basic functions of image processing to be able to see the thing. So this is the image being acquired. Zoom in. Then you can select an area, a specific area to have a zoom in that region. To take the AFM image. Okay, so beside the height, of course, you have amplitude, you have phase, error signal, NSOM has no meaning now because we're not connected to NSOM. It's not an NSOM tip. But you could have up to 16 channels running simultaneously.
Can you monitor them simultaneously, or are you?
Yes,
just
you have to select them in advance. So with the other system you
Okay.
could see here. So now like NSOM is not selected. So you have to select all of these
Okay.
channels from the 16 channels. The interaction is not selected. Okay, so this is the AFM image of this sample. We're scanning now 5 by 5 microns. Okay, so
What's the step size that you're using? You're scanning 5 by 5 microns.
256 by 256 pixels.
Right. Okay, so I can figure out what that is.
It's about 2 nanometers. Okay, so let's stop the scan. It's auto-saved, so we can process it later with advanced image processing. There are different formats for software that you can download freely from the internet also, and so you can do easier image processing or in different systems. We could take like maybe 170 by 170. And this will be like if we want to scan, for example, we can select this area here and here, define the scan. Then we will zoom in and we will scan in an inner area. So this is the, we can adjust the greens. Yeah. Okay. So this is an AFM scan. In fact, when you do NSOM, like in the previous session, you do exactly the same procedure. In terms of AFM, the only thing is that you need to have your fiber connected to the detector, and the detector is aligned. So the output of the detector, it's giving TTL pulse signal. This will be the input here. This is a photon counter, and it will convert it to an analog signal and will send it out to the NSOM as an auxiliary input to the instrument. And then it's synchronized with the AFM. You can see it's a pretty nice resolution. It is 200 nanometers.
What chemical sample are you using?
This is called Fisher sampler.
Okay.
It's used in many applications, like in cells, for example. So they put one layer of polystyrene spheres in a self-assembly process, and then they evacuate, or they put a metal coating, aluminum in this case. So it covers everywhere. Then they lift off the spheres. So you left out with only the metal in the vessels between the spheres. So these triangles are very good because they are very good antennas. In fact, so people done many applications like measuring the plasmons around these triangles. So and you will see them focused into this type of thing. So this is used in plasmonics and used also for tip enhanced harmonics because of this type of thing. I've worked together with one of our customers in Weizmann Institute. Gold is fabricating like triangles at different distances between the apexes. So in fact, you tune the gap of the antenna. Then you see the enhancement effect as you change the distance. So before doing Raman or TERS with this type of measurements, you want to understand how plasmons interact here and what's the nature of these plasmons. So doing NSOM for this structure is very important. This is in fact what he's doing. Okay, so this is the AFM procedure. In fact, so see, there's no optical alignment. Just simply pick and place the tip in there, and the tuning fork will do all that job. So this is the error signal, phase signal, which is signal to the error, in fact. And this is the amplitude. Amplitude will be nice, in fact, to monitor in structures like polymers and silicon. So you would easily see the contrast between the two different materials because of the amplitude decay on the polymer, on top of the polymer side. Okay, so let's stop this. Retract. So the retract is done in two processes. In fact, one side of it is, it's a stepper motor. So before you act the stepper motor, it's rough motion. You bring the piezo down. You retract it down. So it's a gentle retraction, and then you retract with the stepper. Okay. The same for approach. You start with a stepper motor. When the error signal starts to change, it stops, and then the piezo moves to make it to be. So it's a fine engagement between two. Yeah, so this is an AFM, working with two probe systems, just running the other probe and having it aligned with the first probe to do the procedure. So we could do the same with with tip scanning. So just move into upper feedback. So the tip is coming down. Okay. Changing. You see the tip is moving now. It's 3 microns. It's difficult to see from far, in fact. But you can see the sample is fixed. Only the tip is moving. And this will be the profile. So the advantage of doing tip and sample scanning, it's in optics, mainly in optics, is very important. For example, the previous experiment, we have a gold strip and we excited with one probe and we collected with a second probe. So, if you excite a specific location on the sample and you start to move the sample, then you lose coupling. Or you change the boundary conditions if you, for example, excite surface plasmas. So you put it in a specific location, the tip is fixed, the excitation is fixed, the sample is fixed, and the tip is doing tip scanning from this point and far away from it. Okay, so it's very important to have this type of combination, but you still have an access to the lower scanner. So during the scan, you could also move it, or you could move the tip to different location during the scan. So it's limited because it's within the full range of the scanner. But for fine positioning, it's a good tool to use it. Because for those who work with AFM, whatever you do, your area of interest is always at the corner of the image. So you need this possibility to be able to shift it even during the scan to have it there.
Is that the tip sample spacing now?
It's normally, we can measure that in force distance measurement. It's within these conditions of the oscillation amplitude, it's about 10 to 20 millimeters.
Because if you would
So
do
the
it
tip
with
is tapping
a
like
silicon tip, you might crash it. Like
In
just
which case?
moving around.
Yeah, it could be. It could be. So this is operating in. I'm not sure though, because if for the AFM to be established around, you know, in the z-axis, it doesn't matter if the sample is fixed or is moving.
Yeah, true. As long as you don't have big
Half the focus.
height differences, right? And as long as like your feedback is
Quick
fast enough.
Yeah.
Yeah.
Yes, that's right.
Very, very interesting. I think we have to leave.
Okay.
Sorry for that.
Oh, no,
Thanks
thank
a
you
lot
for
the
coming here.
demonstration.
My pleasure.